For our second or last example problem about relative motion of two particles using translating axis, we have at the instance shown in the figure below, cars A and B are traveling with speeds of 18 meters per second and 12 meters per second respectively. Also, at this instant, car A has a decrease in speed of 2 meters per second squared, and car B has an increase in speed of 3 meters per second squared. So what we need to determine here are the velocity and acceleration of B with respect to A or B relative to A. So as shown here on the answers at the right side, what we need to determine later on are both the magnitude and direction of the velocity and acceleration of B with respect to A. So just a solution for this second example problem, before we determine the velocity and acceleration, we need to define the two reference frames like what we did on the first example. So the first reference frame is your fixed reference frame, which is your origin. And the second reference frame is your translating reference frame. So here on your figure, this is your, shown here on your figure rather, we have the X and Y axis here. So this would be considered as your fixed reference frame or your origin. So this is where the fixed observer is located. So meaning is that from this origin or from this fixed reference frame, that is how you observe the motion of your car A or car B. Next, for your second reference frame, which is denoted with a prime, usually with a prime, it is located onto the car A, which it has the X prime and Y prime. And the same of what I explained on the previous lectures about the introduction on the relative motion of two particles using translating axis. So your car A will have the translating reference frame that is attached to or moves with the car A. So from that, this car A will be considered as your translating observer. Now, from the fixed reference frame or your origin, we can identify the velocity of A and the velocity of B. So from the origin going to A, that is your v sub A. From the origin going to car B, that would be your v sub B. And from the translating reference frame, or if ever you are observing on the car A, so from car A going to car B, that will be denoted as the velocity of B relative to A or with respect to A. So from that, we can use that to identify the velocity and acceleration of B with respect to A. So using vector analysis, first, let us determine the velocity. So from the figure, using vector addition, we can write that as vector velocity vector B is equal to velocity vector A plus velocity vector velocity vector B with respect to A or B relative to A. So since what we need to determine is the velocity of B with respect to A, so we need to arrange this equation. So we just transpose the v of A to the other side of your equation. So that will become v of B minus v of A. So since this is in this, the terms here in our equation are vectors, so we need to substitute it in vector form. So we need to determine what would be the vector form of your v of B, or velocity of B, and velocity of A. So let us determine first the vector form for your v of A. So from the figure, kung makita ninyo diri sa figure nato, since it is moving along this road, which is paslant siya, so you can observe that the velocity of A will have two components that would be acting along X and acting along Y. And since the velocity is the 18 meters per second, which is this one, this is the velocity of your A, and it is moving downward, this one, that is the velocity of your A. So if I redraw that, that would be your 18 meters per second. That is the velocity of your car A. So the X component would be acting along the left side, and the Y component would be acting downward. And the angle is the 60 degrees. This is your 60 degrees. So opposite of that would be also equal to 60 degrees. So from that, the velocity vector form of your v of A would be equal to v of AXI plus v of AYJ. So from the illustration here, your both X and Y components are negative because your X component is acting along the left side and the Y component is acting downward. So that would be a negative v of A cosine 60 degrees. I use cosine since the angle 60 degrees is adjacent to your X component, and your Y component would be negative v of A sine 60 degrees since the 60 degrees is opposite to your Y component. And we already know that the velocity of the car A is equal to 18 meters per second. So we just substitute here, so that will become negative 18 cosine 60 degrees I minus 18 sine 60 degrees J. So to simplify, that would be equal to the velocity vector form of your v of A would be equal to negative 9I. So negative 18 cosine 60 degrees would be equal to negative 9 minus 18 times sine 60 degrees would be equal to 15.59 J meters per second. So that would be the vector form of your v of A. Now, for the continuation of our solution, for your vector form of your v of B, since your v of B is moving downward, as shown here on the figure, which is denoted with 12 meters per second, which is moving downward. So the vector form of your v of B would be equal to negative 12 since it is downward, and the unit vector is j only because the direction of your velocity is acting along the y-axis. So that would be equal to negative 12j meter per second. So from the previous equation of your velocity of b with respect to a, which is equal to v sub b minus v sub a, we can substitute the vector forms of this two velocities of your two cars. So your v sub b would be negative 12j minus your v sub a would be equal to negative 9i minus 15.59j. So we can distribute the negative for negative 9i and negative 15.59j. So that will become negative 12j plus 9i plus 15.59j. So you just combine the like terms. So we just combine the negative 12 and 15.59 because they have the same unit vector, which is the j. And therefore, that would be 9i plus 15.59 minus 12j. And the velocity of b with respect to a, or velocity of b relative to a, would be equal to 9i plus 3.59j meter per second. So the answer that we had here is in vector form, so we can determine the magnitude and at the same time the direction. So for the magnitude, using Pythagorean theorem, that would be equal to the square root of your x component squared, which is 9 squared, plus the y component squared, which is 3.59 squared. So therefore, the magnitude of your velocity of b with respect to a would be equal to 9.69 meters per second. So that would be the answer of your magnitude of the velocity of b with respect to a. For the direction, so for the direction, if we illustrate the solved vector form of your velocity of b with respect to a, so both of the components are positive. So we have the x component, which is 9 meters per second, and the y component, which is also acting along the positive y-axis, which is equal to 3.59 meters per second. So this would be your v sub b with respect to a, which is equal to 9.69 meters per second. So the direction that we need to determine here is from the x or horizontal axis going to your v sub b with respect to a, and we will denote that with theta v. And the trigonometric function that we will use here for us to determine the angle theta v is tangent. So that will be tangent theta v. So that is equal to the absolute value of opposite over the adjacent sides. So the opposite would be the y component, and the adjacent would be the x component. So your y component would be 3.59 meters per second, and the y component would be the 9 meters per second. So therefore, your answer for this one would be 0.399. And for us to determine the angle theta, you need to determine the inverse tan of 0.399, and the angle theta of your velocity, which will be the direction of your velocity of B with respect to A, would be equal to 21.75 degrees, which is counterclockwise. So this would be the direction of your velocity of B with respect to A. So again, for the velocity of B with respect to A, the magnitude would be equal to 9.69 meters per second, and the direction would be equal to 21.75 degrees counterclockwise. Now let us proceed on solving the acceleration of B with respect to A. So just a continuation. So for the acceleration, the same thing. If we use the equation from the velocity, which is v sub B is equal to v sub A plus v sub B with respect to A, we will differentiate each term with respect to time or determine the time derivatives. So v sub B will become ace of A is equal to ace of B rather, ace of B equal to ace of A plus ace of B with respect to A, or ace of B relative to A. So again, what we need to determine is the acceleration of B with respect to A. So we just transpose the this term to the left side or to the other side of your equation. So this will become ace of B with respect to A is equal to ace of B minus ace of A. So the same thing of what we did in our solution on finding the velocity, each term are vectors, so we need to substitute the vector form for the acceleration of your car B and the acceleration of your car A. So first is we need to determine what would be the vector form of your acceleration for car A. So based on your illustration, since it is moving or paslant man gihapon pod ato ang car A, or it is moving on a road na paslant siya, and the 2 meters per second squared is moving upward. So this is your acceleration of car A. So the same thing with your velocity, it will have both x and y component. So from this, if we redraw the acceleration of A, which is 2 meters per second squared, so it will have an x component, which is A subscript of ax, and the y component, which is A subscript of ay. And both of the components are positive since the 2 meters per second squared is going upward. And here, the angle would be 60 degrees based from our figure. So from that, the vector form would be equal to a sub x, a subscript of ax I plus a subscript of ay j. So from our figure here, our x component will be using a trigonometric function of cosine since the 60 degrees is adjacent to your x component. So that would be a sub a cosine 60 degrees I plus for the y component, we'll be using sine since the 60 degrees is opposite to your y component. So that would be a of a sine 60 degrees j. And we all know that the acceleration of car A, the magnitude of your acceleration of car A is equal to 2 meters per second squared. So that would be equal to 2 cosine 60 degrees I plus 2 sine 60 degrees j. So from that, the vector form of your acceleration for car A would be equal to 1i, since 2 times cosine 60 degrees would be equal to 1. So that would become I plus 2 times sine 60 degrees would be equal to 1.73. So that will be 1.73 j meters per second squared. So that would be the vector form of your acceleration for car A. Now for car B. For car B is different of what we did to car A. Since we're talking about acceleration, your car B is actually moving in a curved road as shown in the figure. So since it is moving along the curved road, the components here for the acceleration for car B would be the normal and tangential components. So I already discussed about the normal and tangential components before. So I hope that you still remember the normal and tangential components. So for the acceleration for car B, the vector form would be equal to its normal component, so that represented along the x component, plus the tangential component, which is represented along the y-axis. So if we redraw the car B, if this is your car B mismo that is moving along the curved road, so tangential meaning it is tangent to your curved path. So this is your tangential component. And normal meaning that is perpendicular to your curved path. So that would be your normal component of your car B. So for us to determine the normal component, we will use the basic formula, which is the velocity squared over the radius of curvature. So that would be velocity of your car B squared over the radius of curvature. So the velocity of your car B is equal to 12 meters per second. So that is squared. And the radius of curvature given here on our problem, that is equal to 100 meters. So that would be equal to 100. So the normal component would be equal to 1.44 meters per second squared. For the tangential component, since it is acting along the y-axis, your tangential component here, based on our figure, would be equal to 3 meters per second squared. So that would be equal to 3 meters per second squared. And here we can substitute on our vector form for your acceleration for car B. So that would be equal to negative 1.44 I, since the not 1.44, your normal tangential 1.44 rather I, and the sign would be negative since based on our figure here na gidraw nato kanina is acting along the left side, so that would be a negative, and the tangential component would be also negative 3j since the tangential component is acting downward. So that's why both of the components are negative. Both the normal and tangential components are negative. So here, this is your vector form of your acceleration for car B. So we can now substitute in our equation on finding the acceleration of B with respect to A. So just a continuation. So that was A subscript of B with respect to A is equal to A subscript of B minus A subscript of A. So for the vector form of your acceleration for car B rather, that would be equal to negative 1.44 I minus 3j minus the vector form of your acceleration for car A would be equal to I plus 1.73j. So we distribute the negative, so that will become negative 1.44 I minus 3j minus I minus 1.73j. So you just combine the like terms. So we combine the terms with the same variables I and j. So here we have for the I, that would be negative 1.44 and negative 1. And for the j, that would be negative 3 and minus 1.73. Therefore, the acceleration of B with respect to A in vector form would be equal to negative 2.44 I minus 4.73 J meters per second squared. So that is the vector form of your acceleration of B with respect to A. So from that, we can determine the magnitude. So by Pythagorean theorem, that would be equal to the square root of your x component, which is negative 2.44 squared, plus the y component would be negative 4.73 squared. So the magnitude of your acceleration of B with respect to A would be equal to 5.32 meters per second squared. So that would be the magnitude of the acceleration of B with respect to A, or acceleration of B relative to A. And now for the direction. So since this is based from our vector form, the x component is acting along the left side. So this is your 2.44. meters per second squared. And your y component is acting downward, which is the 4.73 meters per second squared. So this is your acceleration of B with respect to A, which is equal to 5.32 meters per second squared. So for the direction, what we need to determine is the angle, and we base it from the horizontal or x-axis. So from the horizontal, going to your 5.32 meters per second squared, this is the direction that we need to determine, and it will be denoted with angle theta A. So based from the figure, we will use the trigonometric function tangent theta A, which is equal to the opposite over the adjacent. So again, we will use absolute value for that. So the opposite would be the y component, and the adjacent would be the x component. So the y component is negative 4.73 since it is acting downward, and the x component is negative 2.44 since it is acting on the left direction. So the answer for the negative 4.73 over negative 2.44 would be 1.939, and we determine the inverse tan for that. So that would be equal to inverse tan of 1.939 would be equal to 62.71 degrees, which is in counterclockwise direction. So that would be the direction of your acceleration of B with respect to A. So again, for the acceleration, so I will just write here. For the acceleration, the magnitude is 5.32 meters per second squared, and its direction, which is denoted with an angle theta A, is equal to 62.71 degrees counterclockwise. So those are the magnitude and direction of your acceleration of B with respect to A, or B relative to A. So that is how you solve for the relative motion of two particles using translating axis.